Hello and welcome to a second lecture on additional effects of the Jeffcott rotor. In this video I would like to discuss three effects, namely the effect of a non-circular shaft, the influence of gravity, and finally inner damping. Why do I include these three cases in this video? Because for all these cases it's necessary to formulate the equations of motion in a body-fixed coordinate system. In contrast to the space-fixed coordinate system that we used until now. And in order to formulate these equations of motion, I will make extensive use of the complex notation, so of complex calculus, so to speak. So therefore this video is somehow or deals with body-fixed coordinates and with the complex notation. So let me start with the first point. So non-circular shafts. And I would like to study the influence of imbalance and also include the influence of gravity here in the study of non-circular shafts. So why are non-circular shafts so important in practice? Well, the most simple answer would be because there is nothing that is perfectly circular. So we have to study the deviations from the perfect circularity. On the one hand, on the other hand, there are a lot of practical reasons to have non-circular shafts, for example, due to keyway or armature windings. So what is now special when you consider non-circular shaft in comparison to the classical circular shaft Jeffcott rotor we discussed until now? Well, you can see the situation here. Keep in mind that all the flexibility is related to the shaft and we are dealing with bending vibrations. So basically we are dealing with a bending beam and just there sits one big mass that exerts a force on that bending beam. And it could be in the middle, it's just a disc, depends on where it is. So what is the bending stiffness of a beam? The bending stiffness of the beam is the product of E and I, Young's modulus on the one hand, and the second moment of area on the other hand. If you have perfect circularity, then the second moment of area is the same in every direction. So you can turn your circle, it will always remain a circle, and so you have perfectly isotropic condition when it comes to the second moment of area. What happens if you have a non-circular shaft? If you have a non-circular shaft, or if you have something else, then the second moment of area in general can be represented by a tensor. So you have principal axis, for example, axis of symmetry as seen here. But in these axes, in these principal axes, the second moment of area might be different. This leads, due to the product of E and I being the bending stiffness, to different bending stiffnesses in the two body-fixed coordinate directions, which are the principal axis for the second moment of area. You can find the principal axis easily if there is symmetry, as in that example, and you can see that the stiffness is completely different, the bending stiffness is completely different in zeta direction and in eta direction. Now, as you can see, these principal axes, they will rotate with the rotation of the rotor. In contrast, of course, to the space-fixed coordinates y and z. In order to introduce these body-fixed dependent or co-rotational dependent coordinates, what we have to do is we have to introduce, first of all, kinematic conditions, and finally in the body-fixed coordinate system, and finally we have to transform our equations of motion that are well known in the space-fixed coordinate system to body-fixed coordinates. And in order to transform the equations of motion, I will use the complex notation because that's much more simpler than working with sine and cosine expressions for the angle omega psi that occurs here between these two coordinate systems. But let me turn first to the kinematic condition that governs that problem here. Namely, well, The kinematic relationship you have also seen before for the classical Jeffcott rotor, the relationship between point W and point S. What's now so special with that kinematic relationship? Well, keep in mind that both points W and S belong to the disk. Yeah? And the disk is modeled as a rigid body. So in a body fixed coordinate system, as we are talking about the material length here between 2 points W and S, which are points on a rigid body, that length has to be constant if it's a rigid body. If the body would deform, of course, that length would be different. That means when you consider the body fixed coordinate system, the geometric relationship between W and S is just a geometric relationship that is independent of time, because we are dealing with a body fixed coordinates here. The relationship can be easily expressed if you introduce the geometric quantities that you see here, namely the radial distance between W and S, so the distance E, and the orientation or the inclination angle of that vector that points from W to S, which is denoted by epsilon. And here it's already stated that epsilon is constant. It's not a time-dependent quantity, as you have seen before for the classical Jeffcott rotor and space-fixed coordinates. So the kinematic relationship is now easily obtained in eta direction. So what you see here is you take the cosine, eta direction is the, well, here pointing, well, at least a little bit to the lateral side. It's the cosine of epsilon and then times E. And for zeta S, we start at zeta V, and then we have to add the sine projection, so E times sine epsilon to arrive at point S. So very easy time-independent kinematic relationships. Now, in order to derive the equations of motion, things are a little bit more involved. And well, for the equations of motion, I would like to introduce a complex notations in order to derive them. So we will start with the space-fixed coordinate system. We summarize the space-fixed coordinates, the lateral and vertical coordinate here, by a complex number. So by adding an imaginary unit I to the Z coordinate, and Rs is then the complex number in space-fixed coordinates. When it comes to the body-fixed coordinates, then the only difference between the space-fixed and the body-fixed coordinates is the factor exponential I omega t, which takes the rotation of the body-fixed coordinate system into account. Again, my two body-fixed coordinates, eta and zeta, are now assembled in a complex number, eta s plus I zeta s, and that complex number is then termed capital R sub s. S stands here for the center of gravity. We will also consider point W, and then we use the same notation, but the index changes from S to W. Why it is so important to have that complex notation? Because, as you can see, the time derivative becomes now quite simple. We are always dealing with exponential functions. Not only the time derivative is quite simple, but also the multiplication by an exponential function is much more simpler than the treatment with cosine and sine terms, and then the use of the classical trigonometric theorems. That's a little bit lengthy. What would now be the starting point for our investigation? So I am studying stationary operation. I start in a space-fixed coordinate system, so with Rs, knowing, of course, the equation of motion in the space-fixed coordinate system. And my first starting point is the following notation here. I have the inertia term, which acts in the center of gravity, S. I have the restoring force, where I do not separate C into C eta and C zeta. We will do that later on. Once we arrived at body-fixed coordinates, we will separate C in C eta and C zeta. And of course, on the other hand, I want to take gravity into account. Gravity acts in the vertical direction only, so in the complex direction I, see the complex unit here times g times the mass of the disk. So this will be the starting point for, again, stationary operation. And you can see that I assemble two equations of motion in one equation of motion in complex notation. So the real part would be one equation of motion and the imaginary part would be the second equation of motion. Now comes the point where I have to replace the lowercase r's here, rs and r sub w, by the uppercase ones. And for r sub s, I have to take the second derivative, and this now becomes especially simple if you use that notation here, that complex notations. Keep in mind that rs, so these body fixed coordinates of the center of gravity, are also space fixed, are also time dependent quantities here, because we are dealing with the bending vibrations. No? So, as you can see, you have to take the derivatives of capital R with respect to time. So as we have to take the second derivative, you see that applying the product rule, you get the classical terms. Take 2 times the time derivative of capital R, then take twice the mixed term, which is then composed by the inner derivative I omega exponential I omega t times the first derivative of rs, and then take twice the inner derivative, which then amounts to I squared, so minus 1 omega squared, and then rs exponential I omega t. Now I insert this result into the equation of motion. I replace at that same time r sub w by, of course, a similar expression to that one here, so by capital R sub w exponential I omega t. And finally, I will move the exponential I omega t on the right-hand side, so I multiply the whole equation by exponential minus I omega t. And the outcome is this one here. Well, maybe there's one step further done. I replaced here again the body fixed complex number by well, its real part and its imaginary part. So let's study that equation in detail. So first of all, we have the second derivative of r sub s. As you can see, this is second derivative of eta s plus I second derivative of zeta s. Next, we have that mixed term plus 2 omega times m, as we are still dealing with the inertia here. Then we have the first derivative of rs, which we have to multiply by I, the imaginary unit. This yields minus zeta s dot plus I, the imaginary unit, times eta s dot. And finally, we have the last term in the inertia part, which is minus omega squared times the mass. And then we have to multiply with that complex number here, which is eta s plus I zeta s. Then we are moving to the second term, c r sub w, which is then just c eta w plus I zeta w, and again exponential I omega t moved to the right-hand side with a negative sign in the exponential function. So we have exponential minus I omega t here. Now we are at the place where we can separate this equation into its real and its imaginary part. So we can split that equation into 2 equations of motion. One equation of motion should govern eta. So you can see it will start with the second derivative of eta, which will be the real part of this equation here. And the second one will deal with the imaginary part and will govern zeta s. So that equation would be, start m eta s double dot. Then from the second part we get minus 2 omega m zeta s dot, which is the second term. The third term will be minus m omega squared eta s. The last term will be on the left hand side, will be c eta sub w. And on the right hand side we will find from Euler's formula here mg sine omega t. The second equation deals with the imaginary part. So we are dealing here with m zeta s double dot plus 2 omega m, or m omega here, eta s dot, minus omega squared plus zeta s, that's the third term. The term corresponding to the restoring force will be c zeta sub w. And on the right hand side we have mg cosine omega t from the Euler formula for the exponential here. And keep in mind you have to multiply that Euler formula with the I here. So therefore also you have a negative sign here, you get a positive sine omega t in the first term. Well, as you can see, this is exactly the point where I replace the c by corresponding stiffnesses in the eta direction and the zeta direction. This is exactly the point where, after all the computations are done, I can introduce direction-dependent stiffnesses. What else can be said about that equation? We have a closer look on that equation. Well, as you can see, the equations are not separated, so they are coupled. They are coupled by the second term, which is the gyroscopic coupling by the Coriolis force. And you might think, but where is the excitation by the imbalance? I can see an excitation by the gravity, which is new, which was not included in the classical Jeffcott rotor, but I can't find my excitation due to the imbalance. Well, we are not yet there. If you look at the indices, then you can see that we are still dealing with body fixed coordinates, but coordinates related to the center of gravity on the one hand, and for the restoring force, we are dealing with complex coordinates, with body fixed coordinates here that are related to the connection point between the shaft and the disc. So what we have to do, we have to use our previously derived kinematic relationship in order to speak with one language and to just include one index here in the equations of motion. And again, we will replace, in order to be able to compare the equations, we will replace index S, so the center of gravity, by index W, so by the connection point between shaft and disc. And this is done on the next slide. So these were our two equations of motion. Let me recall the kinematic relationship. Once again, let me remind that the additional term, the harmonic function here, is a time-independent function, as we are dealing with body-fixed coordinates. And now it's quite simple to apply these two conditions, because, as you can see, we have to replace the second and the first derivative, also the function by itself. But if we take the second derivative of that expression, the last term will always drop out because it's time-independent. Yeah? Also, same, of course, for the first derivative. Yeah? So it's simply an exchange of the index here, because the only quantity on the right-hand side that is time-dependent is eta w and zeta w. So you are allowed to just change the indices here for the second and first derivative. For the quantity eta itself and zeta here, of course, you have to replace it by the sum of eta sub w plus e cosine epsilon, and we will put that term e cosine epsilon because it is not multiplied by any displacements on the right hand side. Yeah? And as there is a negative sign, both equations there, this term will appear with a positive sign on the right hand side. This done, we are arriving at the following equation if we divide these equations then by the mass, in order to get a first term that is independent of any other factor here. Yeah? So we have the second derivative of eta, we have minus 2 times omega zeta sub w in first derivative, plus c eta divided by m minus omega squared eta sub w. And this is equal to e omega squared cosine epsilon plus g sine omega t. And for the second equation, it's nearly the same. It's zeta sub w in second derivative plus 2 times omega eta dot w plus c zeta divided by m minus omega squared zeta sub w e omega squared sine epsilon plus g cosine omega t. I would like to remind again that these equations are coupled, they are not uncoupled. This makes them more difficult perhaps as the equations in space fixed coordinates. Also the derivation is a little bit more involved than the derivation for the classical Jeffcott rotor in space fixed coordinates. What is the advantage of these equations? Well, if they become more difficult on the left-hand side, they become more easier on the right-hand side. So again, a proof of the no free lunch theory. So why is it more easier to deal with that equation for the right-hand side? Because if we leave for the moment gravity aside, we did not consider gravity for the classical Jeffcott rotor, then if you look at that term, it's still something that is time independent. E, the material distance, is time independent. Omega squared is the rotational speed of your rotor. You don't change it because you are in stationary conditions. And the cosine epsilon and the sine epsilon are just the directions that are fixed once and for all times. So, well, that's perhaps the reason why I did not start with that equation from the very beginning. We could have used that equation, body fixed coordinates, to study the classical Jeffcott rotor. But the derivation of the equations of motion is a little bit more involved, and the equations are coupled. So, let me remind that these equations are gyroscopically coupled, and that coupling also exists in the case of a circular shaft. So if you replace C eta by C and C zeta by C. What you could see here is something that could be, or will be, we will show that later on, is a candidate at least for a resonance. At the moment it would be a candidate, I would say, for a natural frequency, C eta by m, and the second candidate would be C zeta by m. We find the same result as in the video before for the flexibility of the bearing, that once you introduce direction-dependent stiffnesses, maybe, we'll see that, you have more than one natural frequency and therefore more than one candidate for a critical speed or for a resonance here. So we have the coupling and we have the excitation by imbalance and by gravity. Now, what should we do with that equation of motion? Of course, we would like to study the influence of all these effects, imbalance and gravity, and especially of the non-circular shaft on, well, the behavior of that rotor. And this is done with respect to the critical speed, so to the resonance. We would like to learn where is the danger of resonance, where could the amplitudes of the solution become larger and larger. You see already that I do not include any damping here. Damping would, of course, make the situation a little bit better. So the amplitudes do not become or do not go to infinity, but they become very large, and that's already enough for an engineer to stay away from the resonance frequencies and from these critical speeds. So I would like to study these critical speeds. As you know, the critical speeds are usually related to the particular solution of these equations. These are still, also they are coupled, these are still ordinary linear ordinary differential equation, second order linear ordinary differential equation. So I will study the particular solution because I assume for the moment that the homogeneous solution decays. Due to the fact that these equations are linear, I can apply the superposition principle and I can study each effect separately. So we will start first to study the influence of the imbalance and then move to the influence of the gravity, the influence of the imbalance being easiest to study because the right-hand side and therefore also the particular solution is a constant. And for the second part, we have classical sine and cosine harmonics, also not difficult to deal with. As I said, we assume here that the homogeneous solution will decay. After we studied the particular solution, I will move to the homogeneous solution and will show to you that this is not always the case. That there are some cases where the homogeneous solution, even the homogeneous solution, may tend to infinity. And this is related to this tiny little stiffness term here, which now looks a little bit more different than before. The difference is in the minus omega squared here. So the stiffness term, the term that is proportional to the displacement, may change due to different rotational speeds here, and it may change even the sign from being positive for very small values of omega to being negative for higher values, supercritical when it comes to a resonance frequency of C eta by m. Then that coefficient will become even negative. And this is a real concern, and we have to deal with that case. Yeah? So let me move now to the study of the particular solution for the imbalance. As I said, this is the particular solution that is particularly simple because the right-hand side is a constant. So we will assume for the particular solution a setting where we just take the same constant here, but of course we have to divide it by that leading factor of eta sub w and zeta sub w. This is easily done. So we get the particular solution due to the time-independent constant excitation here, which is E omega squared cosine epsilon. And just to abbreviate these two natural frequencies, so these two ratios, C sub eta divided by m and C sub zeta divided by m, by omega 1 squared and omega 2 squared, you will find omega 1 squared here and omega 2 squared. And now what you might have supposed until now becomes true. If you look at that expression, then of course the numerator is a constant, the denominator depends on omega and thus will change. And if omega is omega 1 or omega is omega 2, then the denominator vanishes while the numerator is still that constant. So the whole expression, the whole particular solution, either for eta sub w or for zeta sub w, tends to infinity. Resonance. So we identified already two critical speeds here, namely omega being equal to omega 1 and omega being equal to omega 2. And let me remind that this is a similar situation you encountered for flexible bearings. We have non-isotropic conditions, so orthotropic conditions. We have two different stiffnesses in directions, and in this case here in the body fixed directions, and this leads to two different critical speeds. So for the moment this makes sense. If you transfer the results to space-fixed coordinates, then you will see that in space-fixed coordinates you have the classical time dependence cosine omega t and sine omega t from our exponential I omega t here. You will recover these terms. So the solution and the physics, of course, is not different, whether you treat it in body-fixed coordinates or in space-fixed coordinates. Of course, there is an option that one treatment might be more simpler than the other one. I leave the decision to you, whether you prefer to work with constant right-hand sides, but with a more difficult representation due to the coupling of the equation of motion and also with a more difficult derivation of that equation of motion, or whether you prefer the space-fixed coordinates, but the physics, of course, and the final outcome must be the same if we consider an imbalance. And now let's move to the new effect, to the influence of gravity. Now, for the influence of gravity, even when we use space-fixed, body-fixed coordinates, then the right-hand side, the excitation becomes time-dependent. It's a harmonic excitation. But we are happy that we know how to deal with a harmonic excitation for the particular solution. We apply a setting with a sine harmonic and a cosine harmonic. Well, maybe you say, stop. Why do you use the sine harmonic and the cosine harmonic? For my treatment, for example, of the single degree of freedom oscillator, I know that's important to include also a phase shift here. Because there's a first order derivative in that equation. And always if there's a first order derivative, you know that it might not be sufficient to take the sine term into account. There could be also cosine terms appearing once you take the first order derivative. But look again exactly at that equation in more detail. Then what you discover is that in the first equation, you have the first order derivative with respect to zeta. If we set zeta according to its right-hand side to a cosine function, and we take the first order derivative, we arrive at a sine function at zeta sub w omega sine omega t. And by this, the sine function appears in all these terms, and there is no cosine function. So if you make a comparison of the coefficient, then for the sine function, you arrive at an algebraic system that governs the two amplitudes, y, capital Y, and capital Z. The second equation is, of course, obtained by inserting that particular solution in the second equation. And the coefficient of the comparisons for the cosine function of the first equation, which just leads to the simple equation 0 being equal to 0, because there is no cosine term in the first equation, neither on the left-hand side nor, of course, on the right-hand side. Same argument for the sine function with the second equation. If you look at the first order derivative, you can see it's the first order derivative with respect to eta sub w. For our setting, you have to take the first order derivative of the sine function, which is then the cosine function. Okay, so all these terms included into the equations of motion and all the derivations being done, we arrive at the following two algebraic equations that govern capital Y and capital Z. Let's check them once again. So for the first and the last term, I have to set here capital Y sub w sine omega t. Here, after the second derivative, I get a negative sign and the inner derivative omega squared. So this is obviously the first term, while for the second term, I used my abbreviation, omega 1 squared minus omega 2 squared. Of course, in the next step, we can add up that minus omega squared and that minus omega squared to yield minus 2 omega squared. For the term in Z, we refer here to the first order derivative, and there is a negative sign because the derivative of the cosine is minus sinus. And we have a negative sign here, so in total we get a positive sign 2 omega squared Z sub w. And on the right-hand side, we always have our g. Same for the second equation. On the right-hand side, we have our g. Now we have to look at the terms in zeta. For the first term, we have the second derivative of the cosine, which is then minus cosine omega squared Z sub w. And then for the stiffness term, we have omega 2 squared minus omega squared multiplied by Z sub w. And for the term in Y sub w, we have to refer to the first order derivative, and the first order derivative of the sine function is then the cosine function, and there is a 2 omega squared then multiplied by Y sub w. So these are the algebraic equations for the particular solution. We are dealing here with the particular solution, not with the classical eigenvalue problem of a homogeneous solution. As I promised to you, I will discuss that case also, but for the moment we are discussing here the two amplitudes Y sub w and Z sub w. And you see, in contrast to homogeneous differential equations, the right-hand side of that algebraic system does not vanish, is not equal to the zero vector. So these are my two algebraic equations, and I have to solve them. I will use Cramer's rule here to solve these equations, so because the coefficient matrix is just 2 by 2 matrix, but also for another reason. If you use Cramer's rule, then you know that you take the fraction of two determinants, and as we want to study here resonance, so the question is there another resonance? If we study the influence of gravity, then this form is very appropriate because you study the denominator, of course, of that appears in Cramer's rule, which is then the determinant of the coefficient matrix. So let me summarize that procedure. Cramer's rule states if you want to compute capital Y sub W, you take the determinant by replacing 1, namely the first column of the coefficient matrix by the vector of the right hand side, which is just G and G, and then you divide by the determinant of the coefficient matrix, and for Z, in order to determine Z, you replace the second column of the coefficient matrix by GG. You take the determinant and divide by the determinant of the coefficient matrix. So let's state these determinants, or first these matrices, and then we will compute on the next slide the determinants, especially the determinant of delta, which is decisive here if we study the roots of that polynomial in omega in order to find perhaps new critical speeds. So what is the coefficient matrix here? So this equation is, you have to pay attention if you look at that equation, because it's written in a different way, the first equation than the second equation is. Here we start with y and then we have z, and in the second equation we start with z and y. Our vector of amplitudes, so our solution vector, is composed by being the first row being y, the second row being z. So in the first row of my coefficient matrix, I will find omega 1 squared minus 2 omega squared here. In the second row, I will find 2 omega squared there. In the second column, sorry. In the second row of my coefficient matrix, I will start again in the first column with the term in capital Y sub W, so with 2 omega squared here. Second row, second column, I have to use that term here, which amounts to omega 2 squared minus 2 omega squared there. If now I replace the first column by G's, then I arrive at delta sub 1, which is then GG, and then 2 omega squared, omega 2 squared minus 2 omega squared. And if I replace the second column by GG, then the first column is omega 1 squared minus 2 omega squared and 2 omega squared. So now let's have a closer look on that delta, on that determinant, and let's try to compute the values for which that determinant vanishes. Possible candidates for critical speeds. So taking the determinant is, of course, quite simple. You just take the products here. The first product will be omega 1 squared by omega 2 squared. Then we have the terms in omega squared, which are minus 2 omega squared multiplied by omega 1 squared, or omega 2 squared and omega 1 squared. And finally, we would have some terms in omega in fourth power, which would be plus 4 omega in fourth power minus 4 omega in fourth power. So this term vanishes. Instead of writing omega, I wrote omega with an index of g here. And that's the quantity we have to solve for this equation, because I set the determinant already to 0. And that solution omega g would be a candidate for resonance, a candidate for a critical rotational speed. What would be that candidate if we solve for omega g squared? Well, that's quite simple. You have in the numerator omega 1 squared and omega 2 squared, and you divide by 2 times omega 1 squared plus omega 2 squared. So indeed, this is something new. It's neither omega 1 squared, it's neither omega 2 squared. So what is it? Well, if you have a not so perfect circular shaft, so it's a non-circular shaft, but it comes very close to a circular shaft, you will have small deviations between C eta and C zeta, and thus small deviations between omega 1 and omega 2. So what happens if omega 1 is approximately, not exactly, but approximately equal to omega 2? What would be obtained from this term? Well, if we take, let's say, omega k in this case, then we would have omega k in fourth power, and we have to divide by 2 times twice omega k in second power, which is 2 times 2, 4. So it is omega k in fourth power divided by 4 times omega k in second power, which is omega k in second power divided by 4. If we take the square root, then we arrive at omega g being equal to omega k divided by 2. So it's something that is called, for this reason, it's the half critical, because omega 1 and omega 2, they are close together, would be the critical speeds we determined beforehand for the imbalance. And now if gravity comes into play, we find the half critical. That half critical would be a candidate only for a critical speed, because it could be that delta 1 and delta 2 vanish at the same point. That's true for one special case. For the special case, you can do a simple computation here by determining the determinants here. It's true that we have not a resonance, but an expression 0 divided by 0 for the case where omega 1 is exactly omega 2. However, this is an academic case. In practice, you will never have the same stiffness, you will never have isotropic circular condition, perfectly circular conditions for a shaft. You will always have some kind of geometric modifications, or at least some kind of small deviations from circularity. So in all practical cases, if you will do measurements, you will not only see in the measurement the resonance peaks for omega 1 and omega 2, but you will also see higher amplitudes for that half critical values. And these are marked in these waterfall diagrams. So for circular shafts, perfectly circular shafts, you would really also have delta sub 1 equal delta sub 2 equal 0 for omega being exactly equal to omega k divided by p. By 2. And then you would have no resonance, but this is called then an apparent resonance. Apparent in the sense of if you do some measurements, you will find it. And this is the half critical. So let me summarize the results until now. So from the imbalance, so particular solution with respect to the imbalance, we found 2 critical speeds, namely omega 1 and omega 2. And these critical speeds are related to the fact that we have non-isotropic, orthotropic stiffness, bending stiffness conditions due to the non-circularity. If we study the effect of gravity, we will find another critical speed, namely the so-called half critical. And that half critical would not be there for perfectly circular shafts, but it is an apparent resonance. And now let's move to the homogeneous solution. So to study the homogeneous differential equation, here you see the right-hand side is now equal to 0. And first of all, let's have a closer look to that system. I already indicated that there is something not wrong, I would say, with that system, but something that you should focus your attention on, or that I would say there is some kind of alert. You should be alerted if you see this equation. It's a so-called MGK system. What's an MGK system? M stands for the mass matrix, G stands for the gyroscopic matrix, and K stands for the stiffness matrix. The mass matrix is quite simple here. It's just a diagonal matrix with a 1 on the diagonal. So it's the unit matrix. The gyroscopic matrix is a classical skew-symmetric matrix, having the entries -2 omega and 2 omega. Also, nothing to worry about. If you look at the stiffness matrix, then what you can see is, as I said again, you have 2 terms on the diagonal, which are the eigenvalues of that stiffness matrix, and these eigenvalues might change sign. Namely, independence of the rotational speed omega here. And this should alert you, because you know that an MGK system, one can prove this, as purely imaginary eigenvalues for a symmetric positive definite stiffness matrix. If there are purely imaginary eigenvalues, then everything is fine. You usually apply the classical setting with an exponential function. You obtain the eigenvalues that govern the time dependence. If these eigenvalues are purely imaginary, then by applying Euler's theorem on a purely imaginary number, you know that there are the cosine and the sine harmonics, and the cosine is bounded and the sine function is bounded. So everything is nice. However, you see that the system of the stiffness matrix loses its positive definiteness, namely if omega becomes too large. Too large means if it becomes larger than the lowest critical speed here. In the range between the first critical speed and the second critical speed, the stiffness matrix becomes indefinite, because one eigenvalue is positive, the other eigenvalue is negative. If omega is even larger than the second, so the highest critical speed, so we are in the supercritical range, then both coefficients on the diagonal are negative, so you have a negative definite stiffness matrix. And this fact should alert you. So this is the reason we compute now the homogeneous solution for that, or the solution for that homogeneous differential equation by a classical setting. And we would like to determine these values capital omega here. So what do we know about these values capital omega? Well, for the classical setting, where now, as we included here explicitly in the imaginary unit, if we obtain a real value for capital omega, a purely real value for capital omega, everything is okay. Everything is okay because we have an exponential of imaginary unit times the real number times the time, and by Euler formula this amounts to an expression having a sine and a cosine function. As I said, these functions are bounded. If we find a complex solution, then we find a conjugate complex, so we always have a counterpart with the positive imaginary unit, or positive imaginary part, and the negative imaginary part. Now, if you have a negative imaginary part here, then you have to multiply the two i's. They are then -1, and then you have the negative sign of that imaginary part leading a positive factor inside that exponential. And you know, if you have a positive factor times t in the exponential, then that exponential function decreases exponentially, of course, with time, and it will destroy that solution. And as you have to superpose all the solutions here for obtain the general solutions of the solution of the homogeneous dE, then this part of the solution that belongs to the negative imaginary part of capital omega will destroy completely the behavior, in the sense of that you either go to plus or minus infinity here with eta or zeta, and this would destroy your rotor system, if there were no damping, of course. So therefore we have to pay attention to this case. So let's do the computation. Let's find out whether these, here again you can see for omega real we have vibrations, whether this case where omega becomes complex does exist, and whether we are able to relate it to either the, well, we can't relate it, it's true for the positive definite case, but whether we can relate it to the indefinite case or to the negative definite case. Maybe you want a bet. Is it the negative definite case that worries us, or is it the indefinite case that worries us? We will see in a moment. So we want to compute omega, so we insert this setting into the homogeneous differential equation. What do we obtain? We obtain something that looks quite similar to what we obtained before. Maybe the manipulations are now a little bit different because we have the imaginary unit explicitly here in that setting. So from the first term, we take the second derivative with respect to eta. We obtain a minus omega squared From the stiffness term, we have omega 1 squared minus omega 2 squared here, and we multiply by the amplitude C1. From the coupling term, we obtain minus 2 times omega, and by taking the first derivative of the setting for zeta, we obtain I capital omega C2. Second equation works much the same way. We start here with the first order derivative to get 2 omega capital omega times C1 here from taking the first derivative of eta sub w. And for the second term here in C2, so for zeta, we take the second derivative leading to minus capital omega squared, and then we take the stiffness term as being omega 2 squared minus omega squared, and this is multiplied by C2. So we arrive now at a homogeneous, because we are studying the homogeneous differential equation, we arrive at a homogeneous algebraic system. And we are interested in the non-trivial solutions for the two amplitudes C1 and C2, because for the trivial solution everything is clear. You have C1 equal to 0, C2 equal to 0, so eta and zeta will vanish, but this most often does not match to your initial conditions. Yeah. So we are interested in the case where we have non-trivial solutions, and this is the case where our coefficient matrix for this linear system becomes singular, because for a regular coefficient matrix, the only solution, the unique solution of that system is C1 equal to 0 and C2 equal to 0, the trivial solution. And we obtain singularity of the coefficient matrix by arguing that the determinant has to vanish. So now we set the determinant of the coefficient matrix. The coefficient matrix is again here, equal to 0. What do we obtain? We obtain capital omega in fourth power. In second power, we have omega 1 squared and omega 2 squared. We have plus omega 2 squared and plus omega 2 squared times capital omega squared, so twice omega 2 squared. And on the off-diagonal term, and now pay attention to the sign, first the sign is negative. Then we have the imaginary unit and the sign is changed to positive because I squared is minus 1. But because we are dealing with an off-diagonal term, the sign is again negative. So we have minus 4 times omega squared, capital omega squared. And on the diagonal, we had plus 2 times capital omega squared times lowercase omega squared. So the whole amounts to 2 times minus 2 times lowercase omega squared to uppercase omega squared. And finally, we have the term that is independent on capital omega, which is the product of omega 1 squared minus omega squared by omega 2 squared minus omega squared here. You see that what you obtain is a quadratic equation in omega squared. It's a fourth order equation, but you see you only have the even powers here. So you can replace capital omega squared by some other thing and then you have a quadratic equation. From that quadratic equation, it's always important to look at these coefficients here. For the coefficient, which I termed here 2a, one can say that that coefficient is indeed positive because omega 1 squared, omega 2 squared, and 2 omega squared are all positive numbers. Now, let's look at the solution in terms of omega squared. The solution can be written by the classical formula as being a plus or minus square root of a squared minus b. Now what can be said about a and b is that a and b are real numbers. Everything are real parameters here. A is larger than 0 because 2a is larger than 0, of course. And by doing the computations, you can show that a squared is larger than b. So you just multiply all the terms in b. You will find that there are some negative terms here. You take the square of half of that expression here, so the square of a. You compare all the terms, and then you will see that if you do that, on the one column you write a squared, on the other sheet of paper, on another column of your sheet of paper, you write b. And if you compare then these terms, you will discover that there are remaining terms that are either negative for b, or there are additional positive terms for a squared. So you can show that a squared is larger than b. What is the consequence for capital omega? Well, a is positive. That's good, because if a is negative, you would already have a problem, because keep in mind, you should avoid, for stability reasons, you should avoid to have an imaginary part, so not a real solution here for omega squared. So if there's something negative here, then alert, alert. What you see is our setting was exponential of I capital omega t. And once you arrive at something that is negative here on the right hand side, negative for omega squared, then your solution will tend exponentially to infinity, or become very, very large at least. So that's good. We have a positive. Here we have a squared, which is positive and which is larger than b. So you always deduce something here, namely that b. And now it depends on the sign of b, of course, if you really deduce something here, or if you add something. If you really deduce something, so if b is positive, then you obtain two positive real solutions for omega squared. That's good. So everything is purely real here. However, if b happens to be negative, then you have to add something to that a squared. Then of course this term, or the square root here, the second term, will become larger than the a in the first term. But you have to consider two solutions, so also the negative sign here. So one solution will be positive, the other one will be negative if b happens to be negative, and this case has to be avoided. So this is the case where your solution will tend to infinity, where you have a complex valued omega then. So how can we translate this result? So first we state that the radicand must always be, or is always positive. We have a case distinction for b. If b is larger than 0, everything is okay. And this translates to the fact that omega is either less than, let's take omega 1 as being the first, the lowest natural frequency, and omega 2 the higher natural frequency. So omega, your rotational speed, is lower than the first critical speed. So it's really subcritical, in the subcritical range. Then this sign is positive of this term. The first bracket of the second bracket, we also have a positive sign. So b happens to be positive. Everything is nice. Two real positive solutions for omega squared here. Now, second case, if omega happens to be really supercritical, so larger than omega 1 and larger than omega t, let me remind that this kind of stiffness matrix, K matrix, then is negative definite. So even for the negative definite case here, the product of these two terms will have a positive sign. So again, b will have a positive sign. So we obtain two positive solutions for omega squared. So everything is okay because we have two positive real solutions. In the indefinite case, so when we are in between the first and the second critical speed, we should avoid that range. So you should really pass quickly through these two resonance frequencies that are usually very close together. Then b is negative. So this term here will be always, or will be larger than a. And due to the negative sign, you arrive at a negative solution for omega squared. Taking then the square root leads to something that is imaginary, and this really destroys the solution in the sense that your amplitudes tend to infinity, exponentially increasing amplitudes here. So can we study this as engineers in a diagram to visualize that quantity? Well, we can, of course. So what I draw here is omega, the rotational speed. On the other axis, you see the difference of the two stiffness coefficients. So if that difference happens to be 0, you have ideally isotropic conditions. You have the circular shaft. Let me remind that this is just a theoretical result. And for that case, you will find one critical speed. If there is a difference between C zeta and C eta, you will find two critical speeds. The lower one is termed here omega 1, and the upper one is called omega 2. So you can see here omega 1 squared and omega 2 squared, and that axis depicts omega squared. So you can see by increasing the difference, you linearly increase the the second critical speed with respect to omega k squared, and you decrease the second one. In between is, I would call it the death zone, the critical range. And you see it's a critical range, it's a whole range of values, it's an interval of values that you have to avoid. It's the range between these two critical speeds. But why should I want to operate my rotor between these two critical speeds? It makes no sense. That range usually is quite small. So that has to be avoided, that range. And it's exactly the range where the stiffness matrix becomes indefinite and where the homogeneous solution tends to infinity. So the borders of that wedge are the case where you have instability due to so resonance due to an imbalance. In between, you have the range of values where the homogeneous solution becomes or tends to infinity, the amplitudes tend to infinity, and the stiffness matrix becomes then indefinite. Can we translate this result to the case where we have damping? Yes, damping should ameliorate the situation a little bit, and that's here the case. If you have damping, then you will find, well, I would say a small amount of values where you have still decaying free vibrations, so that wedge becomes a little bit less sharp than before, but still there is no reason to use or to operate your rotor in that range here. So damping helps, external damping helps here, and the situation becomes better, but the conclusion, the result from treating the case without any damping still persists. You should not operate your rotor in that range. And well, the last question here related to this is, what happens if I now superpose several effects in order to have a more realistic modeling of my rotor? What would happen if I take elastic bearings into account? Well, if the elasticity is isotropic, you would see the same behavior, just a shift of that critical speed. Here also the starting point of that wedge will shift. It will shift to lower values due to the additional flexibility here. And finally, if you consider orthotropic conditions, and that's very interesting, and it's beyond the scope of that course, you do not obtain, you would say, well, maybe I then obtain, because I have here already for the classical case, I would obtain two wedges, but what you can show is that there are three instability regions that are starting. So three of these wedges. Okay, that's all. Long sequence of a lot of information and derivations for the case of the non-circular shaft, which is a very important case in practice. Now let's move to the case of inner damping. So, why is also inner damping related to body fixed coordinates? But because I would say already the name inner damping tells you it's the damping usually at joints, maybe also the material damping, that it's related to body fixed coordinates and not to space fixed coordinates. So if you have a certain joint, for example, that creates by by some sliding motion creates some kind of damping, then this is related to body fixed to a certain position, so to body fixed coordinates. Opposed to external damping, so for example due to aerodynamics or whatsoever, so some external resistances which are assumed to happen in the space fixed coordinate system, so in the inertia system. So therefore we have to take additional terms in the body fixed velocities into account. So we will have an external damping still related to the space fixed velocities, and we add an additional internal or inner damping that is related now to the velocities in the body fixed coordinate system. Then the first question is, what formulation do I use for the equation of motion? Because now I have two choices. I could choose space fixed coordinate systems, and we learned a lot about the advantages of the space fixed coordinate system for the classical Jeffcott rotors, or I could feel that I'm forced to switch to body fixed coordinates because the inner damping appears here in terms of the body fixed coordinate or the body fixed velocities. And the answer is, we will study this problem still in space fixed coordinates, and we will move, I would say we will move the smaller part, namely these two inner dampings, we will move or represent them in space fixed coordinates. And in order to represent them in space fixed coordinates, guess what? I will use complex notation once again. And that's the reason why this case is also part of this video that I admit becomes longer and longer. So we move from the body fixed coordinate system to the space fixed coordinate system, or we want to move from the body fixed coordinates to the space fixed coordinates. What we do is just we invert the relationship we had before. That's quite simple. You just multiply by the exponential of minus I omega t instead of having exponential I omega t. We have on the right hand side now exponential minus I omega t, and this relates now the space fixed coordinates to the body fixed coordinates. If you have the space fixed coordinates, then they are equal to the body fixed coordinates times exponential I omega t. Yeah? So it's just the sign here that makes the difference. As we want to deal with velocities, we have to take the first order derivative of that expression here. So we take the first order derivative. Don't forget to take the first order derivative of our space fixed coordinates because they are time dependent. So this is done in the first term, and in the second term we take the inner derivative minus I omega. We write down the space fixed coordinates and the exponential here. And now we multiply each term, so the whole equation I could say, by di, and we split the equation in the real part and in the imaginary part in order to find the contribution to the y direction, so space fixed y direction of course, and to the space fixed z direction, so the appropriate contributions from the inner damping. So before I multiply the whole expression now by exponential I omega t, so that on the right hand side we just have these space fixed coordinates multiply with the imaginary unit. So we are really working in the space fixed complex plan. And now we're multiplying the whole equation by d sub I. We arrive then at d sub I y w dot. That's the first contribution, while the second contribution is related to the term z here. I times I is minus 1, so we have a positive sign here, plus omega z sub w in z direction. We also multiply the whole equation by d sub I. We will find the first contribution as the imaginary unit here, di z sub w dot, and minus second contribution will be minus omega yw, this one. And now we fill in these terms into the classical equation of motion, so the equation of motion of the classical Jeffcott rotor. That equation of motion for the stationary operation, of course, we have the inertia term translated or transformed to the coordinates of point W. This leads to the excitation, imbalance excitation, time-dependent imbalance excitation on the right-hand side. We have the contribution from the external damping, dA y dot sub W. We add up the contribution in y direction of the inner damping, so we just enlarge the coefficient by an additional d sub I. And finally, and this is the important contribution, for the stiffness term, we have on the one hand side the restoring force due to the shaft, C times YW, but now we have a coupling, and the coupling is due to the inner damping. It's omega d sub I z sub W. Second equation, we do the same. So we start with the inertia term, we enlarge our damping term, and we add up here the additional contribution from the inner damping to the stiffness term, so to the displacement, which is now minus omega d sub I. So again, you will find a coupling here of the two equations. They are now coupled, and that coupling now happens not as for the gyroscopic case in the velocities by the Coriolis term, but it happens here in the stiffness matrix. And if you imagine how that stiffness matrix would look like, you will find a symmetric part, which is the contribution on the diagonal from the restoring force, so from the classical stiffness, and you find a skew symmetric part, and that skew symmetric part comes from the inner damping. And you can see that that skew symmetric part is variable. It depends on the rotational speed. So depending on the rotational speed, your skew symmetric contribution will vary. And this might cause, again, voice, or might cause situations where amplitudes increase. And now you could guess, is it the homogeneous solution, or is it the solution of the homogeneous system, or is it the solution of the particular solution? And the answer is, maybe you want to think about that question, so you can stop that video here, but the answer is, and I will show that on the last slide, for the particular solution there is no influence of the inner damping. So it's the homogeneous differential equation we have to study. Let's look at the homogeneous differential equation. In matrix form it looks like this. As I said, we have a diagonal mass matrix, we have a very nice diagonal damping matrix, and we have that stiffness matrix that is composed by a symmetric contribution and a skew symmetric contributions, and these off-diagonal terms tend to increase with increasing rotational speed. Now, in order to study the eigenvalues of that equation, I will simplify things by moving again to a complex notation. So this is really the video on complex numbers here in that course. Yeah? So again, I use the complex notation so I can assemble the two equations into one ordinary differential equation, homogeneous ordinary differential equation, homogeneous linear ordinary differential equations, but in complex numbers. Yeah? So here it is. Yeah? Well, if you look at that equation, then of course you see that just by adding that equation, so multiplying the second equation by the imaginary unit and then adding up the two equations, we discover this inertia term that we saw already in that video for the complex notation. We obtain the damping term in complex notation. And now for the stiffness term, things are a little bit more involved. So think of the first part. If you have C in the first equation, you have C y sub W plus omega di z sub W, and you have to add a minus I here in order to arrive at C minus I omega d sub I r sub W at that real part. For the second equation, we would have then the imaginary part, which would be minus I omega d sub I multiplied with y sub W, and C, then of course times I, which is multiplied by ZW, and then you have I and this imaginary unit. Yeah. Okay. This would be the equation in the complex notation. Well, how do we find the solution? Well, the same as before, by using an exponential setting here. So by setting our omega t as c exponential omega t, and we are interested in complex non-trivial solutions, and now you see the advantage of that complex notation. I just have to deal with one single, so scalar, ordinary differential equation, and not I don't have to deal with a 2x2 system anymore. So it's particularly simple to insert the setting into my ordinary differential equation. I just obtain m omega squared plus dA plus di capital omega plus c minus I omega di, and I divide by c times exponential omega t. And this would be my characteristic polynomial in order to determine the capital omega. Now let's have a closer look on that setting here. What is the dangerous case? No? The dangerous case is that case where you get positive real parts for capital omega. So positive real parts for capital omega have to be avoided. The solution of that quadratic equation is not difficult to obtain. However, I would like to simplify the solution a little bit in order to carry out the analytical treatment and to really specify that range of values for which capital omega becomes has a positive real part. So I will neglect quadratic terms in the damping, so second order terms in the damping. How is that done? Well, if you look at the solution, then you might say, well, but I'm missing a term here under the root. Well, this is the reason, because you have to square dA plus di. So we start with dA plus di divided by 2m, and we have plus or minus square root of, we leave out one term, minus 4 times m c minus I omega d sub I divided by 2m. Well, that's nice, but you see that due to the fact that we have a root here, the treatment of that term is a little bit difficult. It's not so obvious what it means to us. So therefore, let's try to find the root under the same assumption as done here by neglecting second order damping terms. This is done on the next slide. Well, first of all, I introduce, I would say, the classical quantities, namely the critical speed here. So I have dA plus di divided by 2m, same as before. And then for the root, I will write that root as being 4 times m squared, minus 4 times m squared, multiplied by c divided by m, which amounts to omega k squared, the critical speed, plus, so minus by minus, plus 4 times m omega d sub I multiplied by the imaginary unit. And I divide the whole expression still by 2m. So what would be a quadratic term that corresponds to the radicand, so that we can easily take the root here, and which is obtained by neglecting squares in the damping, so terms in di squared? Well, I would propose the following one. I would propose ei2m omega k plus di omega by omega k, and the whole expression is then squared. Let's check what we would obtain. If we square the first term, we get minus, due to the imaginary unit, 4m squared omega k squared. Then we have the mixed term. The mixed term is 2 times m omega k, so in total it's 4 times m omega k and the imaginary unit times d sub I, which is here, omega, which is there, divided by omega k, so the omega k in the numerator and denominator will cancel. And the last term is the one I neglect, because it's the square in di. Yeah? And if you now compare this expression to the radicand, Then you see it's the same. So I can replace the radicand, at least approximately, of course, by this expression here. And this allows me, of course, to easily take the root of that expression so that omega 1 and omega 2 are now minus dA plus di divided by 2m plus or minus I 2m omega k plus d sub I eta, the ratio of omega divided by omega k, so the frequency ratio, divided by 2m. Now let's study these eigenvalues. What can be said about the real part of these eigenvalues? So obviously there are two eigenvalues, and these eigenvalues can be split in a real part and an imaginary part. Basically, the imaginary part sits there, second term, first entry in the numerator. So the first eigenvalue is the eigenvalue corresponding to the positive sign here, so corresponding to the case where the imaginary part is equal to omega k. If the imaginary part is equal to omega k, and think of the Euler formula, then what you get is something that is co-rotational, that rotates in the same sense as the rotor rotates, however, with the natural frequency. So this is the co-rotational contribution to the solution. What can be said about the real part of that co-rotational eigenvalue? Well, it's composed by negative sign is here, 1 divided by 2m, which appears in both terms is that factor here. And then we start with a d sub a plus a d sub I. And then now we take a negative sign, because the other negative sign is here, minus eta d sub I. What can be said about the real part? Well, you see that this eigenvalue is really problematic, because the sign of the real part depends on the size of eta. If eta becomes too large, that last part here will dominate, and its sign, the negative sign, will destroy that first negative sign, and the whole real part will become positive. The whole solution will be exponentially increasing. So there is at least one exponentially increasing an eigenvalue which leads to exponentially increasing solution, exponentially increasing time dependence. What about the second eigenvalue? The second eigenvalue belongs not to the negative sign, so to something that for the imaginary part is composed by minus I omega k, so by minus omega k, so it's counter-rotating in the opposite sense of the motion given by the rotor. So it's the counter-rotational part. What can be said about the real part? Well, we start with the same 1 divided by 2m here, and we set that d sub a plus d sub I, and now we have a negative sign, so everything is perfect. We have the negative sign outside here, plus d sub I times eta. So you see that all the terms are negative, no chance for any term here to become positive. So all these terms are positive, but the whole term is negative due to the negative sign here. So no chance for the real part to become positive. So this one, the counter-rotational motion, is stable. The co-rotational motion is not. All depends on the rotational speed. If the rotational speed is too large, then the real part becomes positive, changes sign, and therefore leads to an exponential increasing part of the solution, time dependence of the solution. We will compute these values of eta and also draw them and discuss the conclusion on the next slide. Here you can see again our two eigenvalues. We will focus on the first one. We saw that real part, or we determine the values where that real part becomes positive. So it's exactly the case where eta is larger than 1 plus dA by di. So if eta becomes larger than 1 plus dA by di, then the co-rotational motion becomes unstable in the sense it becomes exponentially increasing. This is the case if there is no external damping at all, This is the case in the whole supercritical range. So if you have inner damping, you cannot use the whole supercritical range, which would be catastrophic, right? So we will discuss, of course, also countermeasures to that. So let me summarize these results. The first one is the skew symmetrical part of the stiffness matrix leads to at least one eigenvalue that have a positive real part. At least this case is possible. And we see that it depends on this condition. This condition clearly says if there is no, or if there were no external damping, and there's always some external damping, that's good, that saves us. If there were no external damping, no stable operation would be possible for values of eta larger than 1, which is beyond the critical speed omega sub k, which is the natural frequency of the Jeffcott rotor. Now, if there is external damping, it shifts the critical velocities to higher rotational speeds. However, external damping is usually accepted, but it's unwanted. You don't want to increase artificially the damping in the system just to be able to use the supercritical range. That's not energy efficient. So what can you do instead? Let's discuss this on the next slide. So first, let me show the stability diagram. So I plot here eta and the ratio of dA by di, and the unstable range is limited, bounded by a straight line which starts at values eta equal 1 here, and then it follows just a linear function, just the ratio dA by di. So one possibility to stabilize the rotor is to lower di. How can I reduce the inner damping? Well, I avoid everything that rubs, that slides, and so on. So I avoid pinch fits. Must be really tight shrink fits, and you know that if you assemble a rotor, then you cool the parts in order to be able to fit them together. That this manufacturing procedure is quite involved, and this pays off. You really have to reduce your inner damping. This diagram is the reason for this, why you do this. You have to reduce the inner damping not because you want to be very energy efficient, but because you want to increase the stable domain, the ratio dA by di. However, there might be limits to this, and then you can, I would say, in exceptional conditions and in exceptional cases, you will increase the external damping. For example, by introducing auxiliary ball bearings or auxiliary bearings that are supported by an elastomer in order to support the system with a high damping module. But you want to use this in extreme cases. For example, if you pass the resonance in order to avoid that the amplitudes become too large. But once you have passed the resonance case, you want to be in a stable situation, stable stationary state, and then you don't want to use these auxiliary bearings. They are really designed for special situations, for safety relevant cases and so on. And finally, you can also try to increase the natural frequency of the system, but then this leads or could lead to a subcritical operation in order to make that range of possible values for your rotational speed larger and to increase the range of values. Well, the last question, how about the particular solution? Well, is there no influence of the internal damping on the particular solution? Well, if we look at now the whole equation of motion with its right-hand side, you want to apply a setting according to the right-hand side in order to determine the particular solution. So let's make such a setting. Let's set a particular solution R sub p equal to some kind of amplitude r times exponential of I omega t. You take the first derivative of that setting, you insert it into this equation here. R is some time-independent amplitude here. So if you insert that setting and take the first derivative, you arrive here for the inner damping at the term I omega r exponential I omega t. if you consider the displacement related contribution of the inner damping, you see it appears with the opposed sign, minus I omega d sub I Rp, which is then capital R exponential I omega t. So what you observe is that both contributions cancel, and therewith the whole influence, the whole parameter di does not play any role for that equation anymore. The contribution for d sub I will cancel, and the solution, the particular solution, will be independent on the inner damping. So the terms with inner damping cancel, and there is no influence. That's the final result. That's the reason why we treated the homogeneous solution. There was an influence, a big influence. I would say even tremendous influence. A whole range of values, a large part of the supercritical range is not usable. But for the particular solution, there is no influence. Well, this is the end of my talk. This is the end of that presentation on, I would say, two big effects. The one is the non-circular shaft, of course, together with the influence of gravity. And the second one is the inner damping. And for all these discussions, you need complex numbers. You see the importance, how they reduce the complexity and mathematical complexity in the operations when you use clever calculus. Yeah? Well, in the next video, I would like to turn to another problem, namely to the problem that you have a slanted disk, and it's a problem where we have to make less use of complex numbers, but more use of arguments related to strength of materials. You have to extend a little bit the system from a 2x2 system to a larger system, 4x4. And all this is done in the next video, which is the last video on these special effects. So thank you very much for your attention, and see you in the next video.